Okay, so we started with the reciprocal parent function. This is the first graph that is discontinuous. Okay? Notice up here in the definition, it says that x cannot be 0 because that would mean you divide by 0, and that is undefined. Okay? Which means we're going to have a discontinuity when we try to graph this. Each piece of the graph is called a branch. We're going to have an asymptote in this graph, which is a line that the graph approaches. Approaches means gets close to. Can you touch it? Sure. You just get close to it. You want to get close enough to touch it? Doesn't matter. Okay? You get close to that line. We have 3 different shapes of asymptotes that we're going to work with. Vertical, horizontal, and slanted. Okay? So we started by making a small table of values here. So let's go ahead and we'll start in the middle and we'll do the positives, and then we'll come back and we'll do the negatives. If I plug in 0, and this is the reciprocal parent function, we get undefined. Okay, so I'm just going to put undefined. Yeah, undefined. Because dividing by 0 is not defined. Okay? This is where your vertical asymptote comes in. Right here at the x-coordinate of 0. This is where the color is. The reason I want a color is because it's kind of hard to see. If your marker is really thin, it goes right over the grid line and you don't even see it. Okay? It's usually a dotted line, but I'm just using a highlighter, so mine's a solid one here. And I'm just going to write the equation of that asymptote right next to where I wrote it. So this is x equals 0. It's a vertical line. Okay, that is going to be our asymptote. That's why it's in a separate color. Okay, so let's just plot a few of our points. These are your parent points. You're not memorizing them. They should make sense once we find a few of them. Okay, 1 divided by 1/2. 2. What's the reciprocal of 1/2? Say it again. 2. Oh, it's a reciprocal parent function, so you mean that I plot the reciprocal? Yes. What's the reciprocal of 1/2? 2. It's the reciprocal parent function. What do you plot when you graph a square root? Square root numbers? 4, 2, 9, 3. It's the reciprocal function, which means you plot the reciprocal. What's the reciprocal of 1? Just 1. Okay? Now I'm plotting extra points here. Usually we just pick 1 point per section or per branch. 2, 1/2. Infinity is in there to throw you off just a wee bit. Not quite. Think about it. What if I plug in 10? 1/10. 20. 1/20. 1 over, okay, so what's 1 divided by infinity? Not quite. All right, hold on. Let's go back to like kindergarten. Hold on. Right? My kindergartner just told me about infinity, and he's got it a little bit wrong, but that's okay. How can you divide something into infinity parts? How many is going to be in each part? Infinity. Okay, hold on. Hold on. Here is your pie. Here is 2 slices of pie. Here is 4 slices of pie. What if I made infinity slices of pie? How big is each slice?
1 infinity. 1 infinity.
Can you give me an estimate of a number on the number line? You can. What? Too small. What is too small? 0? Your piece is like non-existent. It's 0. There's almost no piece if you keep slicing this up. Okay. The piece is getting too small. It has to be small. Okay. It's almost 0. Almost. Look at this. An asymptote is a line that approaches the graph is getting close to 0. Maybe. It's getting close to 0. Okay? Close to 0. Can it be 0?
No.
No. Because you can't do the reciprocal of that. No, it won't happen. Okay. Now let's plot these positive points and let's see what shape this creates. 1/2, 2, 1, 1. Oh, okay. Well, if I did 3, I would get 1/3, and we keep going. You're going to get, this is where your horizontal asymptote is going to come in. It's going to go right here. The asymptote is meant to represent that line that the graph is getting close to. We just kind of talked about close to 0 here. Okay? Now this is y equals 0. These are just guidelines. And what happened is I just divided my graph up into the 4 quadrants, and I'm plotting points in the top right quadrant. I'm going to draw the shape for you. It's a parent function shape. It's a new shape. I'm going to show you what it looks like. We've got a few points to help guide us. You're going to start up here by this arrow in the quadrant 1. It's a nice, curved, smooth shape that looks like it levels out as I go towards my asymptotes. I'm getting close to my asymptotes. In this particular case, I'm not actually going to touch the asymptote because I've reasoned through this. I'm not going to get 0 as my output because we can see that it's not possible for this equation. Yes?
Isn't there a name for that?
Yes, it's actually called a hyperbola. Yeah, from conics. But this hyperbola is square as opposed to like slanted like some of the other ones we were doing. It is called a hyperbola shape. Yeah. Wait about 2 minutes.
Isn't it supposed to keep getting smaller?
It is, but it's too hard to draw that. That's why the asymptote is there. You're meant to get closer and closer and closer to the asymptote. It's too hard to draw it and actually show it getting closer. So that's why the asymptote is there. Okay, negative numbers. We have a whole set of values. Let's plot them and see where this shape goes. -2, -1, -1/2. Okay, 1 over infinity is still very, very close to 0. Close to 0. And so I'm actually going to plot the points that I have here. And this is going to be a symmetric shape to what's in quadrant 1. This one just happens to be in quadrant 3. Because if you're reciprocal a negative number, it's still negative. This is your parent shape. That's it. It's kind of like a curved L shape with arrows, maybe sort of a C-looking shape. It fits into quadrant 1 and 3 very nicely. Now, which points do I usually plot for my parent? You only need 1 per branch. You plot as many as you feel comfortable with. I need to see 1. Okay? Most of the time, we do that 1 point because it's really easy to remember. Okay? That's pretty much it. That's the point that I aim for. If you need more, you use more. Okay? But they get really small and really big really fast, so it's hard to show more of them. Okay, we're going to write in the domain and range because I've got 2 pieces of the graph. I'm going to have 2 pieces of domain and range. Okay, so the first one is going to go -infinity to 0, union. 0, all open. We go left to right on the graph. Yep.
So I understand where you got the negative infinity, but when did it go to like, is it just like how did you get to 0?
what's 1 divided into an infinite number of parts? But not almost 0. Okay? Now, next to the domain, we are going to write vertical asymptote, VA, abbreviation, x equals 0. I just want you to see the asymptote connected to the domain because they're similar. All right, next one, range, negative infinity, 0, union, 0, positive infinity. Now I'm looking at my y value, so I'm going to drag that horizontal line. I'm negative infinity. Up, pick your pencil up. The graph is discontinuous. I pick my pencil up and I skip the y value of 0. And then I start at just above 0 and it goes up to positive infinity. This is the range in quadrant 3. This is the range for the branch in quadrant 1. There is no overlap, so I have 2 separate pieces. Discontinuous graphs can have multiple pieces for domain and range. Okay? Based on how it does or does not overlap.
If the graph, like if the points themselves are like if they're both like 1 or -1, why can't you just say like negative infinity to -1? Because
The graph doesn't stop at -1. Look, the graph actually goes from negative infinity y coordinate up, getting closer to 0, as close as possible to 0, but not including 0.
yeah, but for the domain, like
Okay, look, where does it stop? Negative infinity for x is moving, really close to x equals 0, but not touching it. Because I can't divide by 0. Then I pick my pencil up. That's where we get the union. And we start at close to 0 on the right side, all the way to positive infinity.
Why did we highlight the yellow?
Usually you don't plot that many points for a parent function. You just need 1 per branch. That's the easiest point to try to plot, right? 1, 1, 2, 4. Okay? 1, 1, -1, -1. That's it. Okay. Horizontal asymptote, HA, y equals 0. Notice that we are skipping over our horizontal asymptote in the range. There are some connections between the asymptotes and the domain and range.
So it's vertical asymptote?
Vertical asymptote is for the x equals. Horizontal asymptote is for the y equals. Question?
Why do you need to use, what's the other side instead of the inside?
Or intersection? We don't.
Both work together.
No, do a union. Okay. Turn your page. Right, page 2. Okay, page 2. Ooh, A, H, and K. They do the exact same thing as they've done for the rest of the year. Okay. Now, I am going to say the center of this graph is at 0, 0. We'll get to the examples right after this page, okay? Stretch, compress, and reflect. Okay? Moves the graph right or left. All right, look at the h value. It's next to the x. There's one other thing we're going to say about the h. Okay, this is going to be your vertical asymptote for your transformations. Notice up here in the description, it says that x can't be h because that would mean I divide by 0. dividing by 0 is what's creating the vertical asymptote because it's undefined. Means you have to pick your pencil up and not draw anything there. That's why you get the vertical asymptote. Undefined appears as a vertical asymptote on the graph. Okay, K, right? That's the K number.
I don't understand that sentence. I'm gonna try to.
Okay, so if you were to plug in H, you would get divide by 0.
Oh.
That's what causes the vertical asymptote. Right? On our table of values, the undefined, that's what causes the vertical asymptote.
Oh, so plugging in H would mean. Okay, so would
Yep.
it be a vertical?
Yeah, we're going to draw one. Moves the graph up or down. Okay? And this is going to move our horizontal asymptote also. It's the vertical asymptote, the dotted line. We're not actually going to graph anything there. Okay. We're going to do an example, and then you'll see where these values come in.
So it's basically our normal transformation equation.
Yes. Except this time we have to transform our asymptotes also. Everything has to move when we do a transformation. Up, down, right, left. The asymptotes are part of the parent. So if I'm going to shift the parent graph, I have to shift my asymptotes also. Yeah. U, union. Okay? And then I'm going to write VA x equals H. Notice for the parent function, that vertical asymptote number, that's the dividing part for my graph. That's the first branch and then the second branch. Okay. All right, we're so close to putting it all together.
Oh, well, that's only on the parent.
Okay, so we're going to describe it. Crosses the x-axis. Crosses the x-axis. Now I'm going to write the coordinate down. An x-intercept is an actual point on the graph. So I'm going to write it as a point. That would be the coordinates, x, comma, 0. How would you find that?
You like multiply solve
Multiply
it
that
out.
from the density ratio.
Like solve. You
Put 0 in for
foil.
Yeah, there we go. Okay. Plug 0 in for y. If I give you one coordinate, you can plug in and solve for the missing coordinate. Okay? Y-intercept crosses the y-axis. Okay? 0 comma y. This one's a little easier because notice that x-intercepts has a plural, right? I could have more than one of them, but x-intercept, singular. There's only one. There's only one point that's going to cross the y-axis. And this is plug 0 in for x. Sometimes that looks like this. F of 0, right? That's function notation. Means plug in 0 for x. Graph write the domain and range, sketch the vertical and horizontal asymptotes. So now I'm going to look at this and I'm going to write my transformation. Right 4 up 2. From the center. The origin is the place that you are moving. So I'm going to go right 1, 2, 3, 4 up 2. I'm just going to do a little open circle just to mark the center of my graph. That's where your asymptotes move to. And so I have my colored marker or pen. I'm going to draw my asymptotes. X equals 4. There's my asymptote equation. Y equals 2. And I'm just going to record that information here. And I'm sort of going to check things off as I do them, just to make sure I don't leave anything off. Okay. Vertical asymptote, x equals 4. Horizontal, y equals 2. Okay. Next, can I do domain and range? Yes, I can do that. Okay. Let's do that underneath of the graph. Domain, right, because it's connected to my asymptotes. Negative infinity to 4, union 4 to positive infinity. Okay, range connected to the horizontal. Now we always go in order of the number line. So negative infinities come first. Okay, negative infinity comes first, all the way up to positive infinity in order. So my horizontal asymptote is 2. To positive infinity. We'll just scooch this equation over. There you go. All right, I wrote down my domain and range. Let's sketch the graph.
Will the domain and range ever not be in that format? With the
Maybe on the... No, these numbers are always going to be the same. The 4, 4, the 2, 2. Because all we're doing is we're just skipping over the asymptotes when we draw this.
Is there a reason you're not using brackets?
Okay, infinity is always open. Did you include 4? Are you plotting any point with the x-coordinate of 4? No, that's why it's open. Yeah. Yeah, that's a 4. There's an arrow hiding in there. There you go. It's a 4. Yes. Okay. Graph. My parent function points say over 1, up 1. Right there. Could you graph more points? Sure. You only need 1 per branch. If you're not comfortable with 1 per branch, you plot more. So maybe I do 2 and 1/2. 1/2 and 2. Here's the shape. Okay, I'm only going to check 1 point per branch. If you need more, you plot more. That's the shape. That's it. All we did is we moved the center of my graph and drew the same shape. There's no stretch. The A value was 1. Nothing changes on those counts. Okay, check. I have my graph. Ooh, X and Y intercepts. Now I see them on the graph, right? A little less than 2 and a little less than 4. But I want real numbers.
If you can use your counts, can you figure out the...
Yes, you can.
You just plug in X
If-
only for the X intercept.
No, you could do it for both. You just have to get a little creative and go backwards. Okay? Yes, you can plug it in. Yes, you can use counts. I don't care which. Doesn't matter. I just need them labeled accurately. And so I'm going to plug it in, and I'm going to do the y-intercept first because it's a little more straightforward. F of 0 equals, so negative 1/4 plus 2 is 7/4. Yeah, fractions. You can do it. Because I'm finding, yeah? Okay. So 0 7/4 is my y-intercept. Okay, there's 1 point. Right, there's my 1 point on the graph. It's kind of messy to label my points over the grid, so I'm just writing it up top so I can see it. Okay, x-intercept. Well, if I look at my booklet, it says plug in 0 for y. Okay, plug in 0 for y. Yeah, so it takes a little bit of solving, a little bit. You might even be able to just guess and check that number. Maybe. Okay, so I'm going to minus 2 to the other side. Do a little cross multiply and then solve for x. So I get 7/2, 3.5. Looks about right. I already have them on the graph. So I subtract 8. And I divide by -2.
Oh, you crossed it over.
Yeah.
So that equation is already set up to
Yeah. Yeah. Well, you just plug in 0 for y from the starting point, and it's going to take just a little bit of work. So 1 step, 2 step, okay, 2 steps to get to something that you could do in your head.
Is there a reason why the numerator was the same for y-intercept?
No reason. Okay, so I'm just going to label it. So we have 7/2 and 0. So there are my 2 intercepts. All right, let's go in order. Here is my parent function. There it is. There's my parent function. I need to go left 3. Okay, so I'm going to go in order. Reflect, stretch, left 3. So here's how it's going to happen. Reflect. So now my parent function, right now it's in quadrant 2 and 4. Stretch and left 3. 1, 2, 3. That is the basic shape that I am aiming for. Notice the reflection switches which quadrants I'm going to be drawing my graph in.
Isn't the stretch going to make it wider?
It's going to make it taller looking. Okay? And so, yeah, my points are going to change just slightly because this is just kind of an estimate here. And so instead of 1, 1, it's going to be over 1, 2. That's where it's going to go instead. It's going to be, that first point's going to be a little bit further away from the asymptote. Okay? And we're going to write it. We'll write the points out. I don't write the left, right, up, down, but I will write out the stretch. Okay? So let's graph it. I'm going to write down my transformation. Reflect over x. Stretch by 2 and left 3. All right, so that gives me a vertical asymptote. X equals -3. Okay. X equals -3. Ooh. There's no up or down. That means my asymptote staying at 0. Okay. And stretch. See what we can do for our stretch. Okay.
No, I'm not doing it. I'm not gonna have something to do.
Bring it back. Okay, I wrote down my parent function points. Notice I only gave you one per branch. You don't need more than 1 point per branch. Stretch and reflect, so I'm going to multiply by the -2. Those are the parent function points. So when I count those points, it's going to be in relation to the center of the asymptotes, right where those asymptotes cross. Okay, so we have from the center, that's why I put the 0 here, that's the center of the graph, that's where that asymptote occurs. -1, +2. -1, +2. Just 1 point per branch. If you're not sure, count more points. Two over 2, 1/2, but doubled is 1. I don't usually write my table of points. I just reciprocal them and multiply. Think of my parent function. I reflected it, so I have to be in the top left portion.
So what you're gonna do, you're just gonna put down 1 point and then just estimate the rest.
Yes, exactly. 1 point, estimate the rest. Because I've got guidelines. I have asymptotes to help contain the curve where it's supposed to go.
But you have to make sure that it gets closer to the line.
Yes, it should. That's the definition of our asymptote. If we have asymptotes, draw the graph to get closer to the asymptotes. Yeah.
So you take, so the points that you draw is -2, or -1, 2, and 1, -2, and then you do that based on where you drew the inclines rather than the actual.
Yes. You always count from the center of the graph. All I did is I moved my center. Yes. Okay, let me draw the other one and then we'll get your question. 1, -2. So over 1, down 2. Notice that's a 1-2 count. Because it's a reciprocal, you can actually do a 2-1 count also. So every point can actually get you a second point.
Wait, so it would go from -3 to -4, or would it still be that? Never mind.
Okay. Yes, Wadey, what's your question?
So how would you use exit?
X-intercept, there wouldn't be any in this particular case because I'm looking at the graph. So I would just say none. Based on where that asymptote is, I'm like, yeah, it's not going to happen. So that's why I like to sketch the picture and be like, okay, I think I should solve for them because I see them on my graph. I don't see it, I would just say none. So I'm not gonna list it. There aren't any, but I will find my y-intercept. This one's pretty straightforward. -2/3. There's nothing to simplify. You just look at it and plug it in. Okay?